How to score a probabilistic forecast. On November 7, 2016, eve of the United States presidential election, Nate Silver's website 538 published that Hillary Clinton had a 72% chance of winning the presidency. As we all know, Donald Trump won, and Nate Silver's forecast was labeled as wrong. But wait a second. What exactly is a wrong forecast anyway? Before we answer this question, let's first define how we are going to use some terms, at least in this video. We call your attention to the fact that our interpretation of the concepts we are about to define are not accepted by all experts of the field, but at least this will avoid misunderstandings that will only prevent us to reach conclusions straightforwardly and without contradictions. We will say that an event or statement is random if we cannot say in advance, with full certainty, what its result was or will be. Thus, by our definition, a random event may be something that already happened, like the final score or result of a basketball game we didn't watch, read, or heard about. We will also define, or rather interpret, probability as the degree of belief someone has in the occurrence or veracity of a random event or statement. This means that if you say that on election day your probability that Clinton would win was 72%, you should be willing to pay a maximum of $72 for a contract that would entitle you to receive $100 in case she won. Given those definitions, the outcome of the US presidential election on election day was a random event that could end only in one out of two possible results: victory of the Democrat candidate or victory of the Republican candidate. Therefore, we're not considering the possibility of a tie or the possibility that another candidate that's neither Republican nor Democrat could win the election. Okay, now we can try to answer our initial question. What exactly is a wrong forecast? One criterion to qualify a probabilistic forecast about a random event that has only two possible results may be the following. If the result that has the larger probability assigned by the forecast, that is, more than 50% in the case of the US presidential election as we are considering it here, do not happen, then the forecast is considered wrong. Otherwise, it is considered right. If the forecast assigns equal probability to all possible results, 50% in the election example, it's neither right nor wrong. Let's say it's neutral in this case. Although this criterion seems intuitive, it has at least one undesirable feature. Realize that, consider two forecasts. One assigned Hillary a 90% chance of winning, and another a 51% chance of winning. By the criterion we established before, and by which Nate Silver's forecast was considered wrong, both forecasts are equally bad. However, it seems evident that the forecast that assigned a 51% probability to Hillary's victory is better than the one that assigned a 90% chance to her victory. We can say so because the second forecast is, in a way that we have to clearly specify, closer to the event that happened, that is, Trump's victory. Therefore, a much better way to qualify probabilistic forecasts is to score them instead of just saying they are right or wrong. That insight came from meteorology, a field in which forecasts play a significant role, and was mathematically formalized in a paper written by a researcher named Glenn Breyer, published in 1950. He proposed a score function, nowadays named after him, based on the intuitive notion of Euclidean distance between two vectors or points. It is in fact the square of the Euclidean distance, thus avoiding the computation of square roots. For this reason, the function is also called quadratic score. To understand Breyer's metric, let's consider the example of the US presidential election once more. Let's use the three forecasts mentioned earlier. Forecaster A assigned a 72% probability to a Hillary victory, forecaster B assigned a 90% chance, and forecaster C a 51% chance to the same result. Since in this case the random event had only two possible outcomes, we may represent them as the extremes of a straight line of unit length. If point 0 represents a Republican's victory and point 1 a Democrat's victory, a valid forecast is represented by a point on this unit length line, extremes included. After representing the three mentioned forecasts, we only need to compute the squared distance between the forecast and the verified result. In our example, point 0, that represents Trump's victory. Thus, forecaster A had a score of 0.72 squared, forecaster B a score of 0.9 squared, and forecaster C a score of 0.51 squared. Notice that using Breyer's score, the smaller the score, the better it is. A perfect forecast has a 0 score, and the worst score is 1. If you don't like this, just use the negative of the squared distance. Then all the scores will be between -1 and 0, and the larger the score, the better it is. With all that said, we conclude that forecaster C presented best forecast, at least according to the Breyer score. Just to make sure the concept is clear, imagine now the alternative scenario, a Democrat's victory. In this case, the score of forecaster A would be 0.28 squared, the squared distance between 0.1 and 0.72. The score of forecaster B would be 0.1 squared, and of forecaster C would be 0.49 squared. Thus, if Hillary had won, forecaster B would have the best score, since it was closer, by the Euclidean distance, than the other forecasts to the verified result. The Breyer score can be easily generalized for random events with more than two possible outcomes. A simple instance is a football or soccer match. It may end with the victory of the home team, with the victory of the visiting team, or it may end tied. In this case, a valid forecast is a triple of real numbers all between 0 and 1 that add up to 1. Let's illustrate the Breyer score for a football match using numerical examples once more. The present world champions, France, will play against Iceland in Reykjavik, Iceland's capital. Forecaster A believes that Iceland has a 20% chance of winning, France has a 50% chance of winning, and there's a 30% chance that the match will end tied. Forecaster B attaches 10% chance to Iceland, 65% to a French victory, and 25% chance to a tie. And forecaster C assigns 12% to Iceland, 70% to France, and the remaining 18% to a tie. Notice that each forecast may be represented by a three-dimensional vector of non-negative real numbers that add up to 1. Therefore, for random events with three possible outcomes, a valid forecast can be graphically represented in a ternary plot. This plot is a surface called simplex, the subset of the 3D real space in which all the three components of a 3D vector are non-negative and add up 1. This vertex represents the result Iceland wins. This vertex represents the result France wins, and this represents a tie. Each point on this surface is a valid forecast, so that in our example you have 3 points representing the forecasts or forecasters A, B, and C. The triangle representing the simplex may be rescaled to have a unit height, so that each valid forecast is such that the sum of the three heights from the forecast to each of the sides of the triangle is 1. This means that each height represents the probability assigned to the result represented by the vertex opposing that height. To see this, let's consider forecasters A values, represented by this red dot. The distance from the dot to this side, opposing the vertex that represents the result Iceland wins, is 0.2, the probability assigned to an Icelandic victory. The distance from the dot to this side that opposes the vertex France wins is 0.5, representing the probability assigned to the result France wins. Finally, the distance from the dot to this side represents the probability assigned to the outcome tie. An interesting feature of this graph is that for any point inside the triangle or on its edges, the sum of the three heights is 1, exactly as required by probabilities assigned to three mutually exclusive results of which one and only one will happen. After displaying the other two forecasts, let's assume that the match ended tied. Which forecast was better, that is, had the smaller Breyer score? Looking at the ternary plot, we already have an idea, but to compute the score correctly, let's consider the simplex once more. The result tie is the point 0, 1, 0 on the 3D space, while forecast A is the point 0.2, 0.3, 0.5. The squared Euclidean distance between the forecast and the verified outcome is therefore 0 minus 0.2 squared plus 1 minus 0.3 squared plus 0 minus 0.5 squared, resulting in a score of 0.78. Computing the scores of forecasters B and C in the same way, we get 0.9851 and 1.2068 respectively, meaning that forecaster A suggested the best forecast according to the Breyer score. This shows our intuition was right. Forecaster A was closer than the two other to the tie vertex, the verified outcome. Other than its intuition, the Breyer or quadratic score has another interesting property. Forecasters must communicate their true probabilities. Remember, we are considering them as degrees of belief, in order to minimize the expected score they will get. That is, the Breyer metric discourages cheating. By cheater, I mean a forecaster that tries to fool the system, communicating a forecast that in fact is not believed by him or her, only to minimize his or her score. Let's prove this result using the forecasts for the hypothetical football match, Iceland versus France. Notice that the score of a forecast, before we know the final result of the match, is a random variable that may assume any value between 0 for the best score and 2 for the worst score. Now we need to introduce some mathematical notation. Let the vector f, f1, f2, f3 be the vector with your forecasts, that is, your announced probabilities for the three possible outcomes of the match. Notice that you can lie, so f may be different than your truly believed probabilities, which we'll denote by p. Like p1, p2, and p3, a valid forecast must be such that f1, f2, and f3 are all non-negative numbers that add up to 1. The final result of the match will be denoted by the three-dimensional vector r, with entries r1, r2, and r3, in which r1 will be equal to 1 and the other entries will be 0 when the home team wins, or r2 will be 1 and the other entries 0 when the match ends tied, or r3 will be 1 and the other entries 0 when the visiting team wins. In this framework, the Breyer score of a given forecast f for a match with result r, denoted S of f and r, is equal to f1 minus r1 squared plus f2 minus r2 squared plus f3 minus r3 squared. And the expected score of the same forecast will be, or developing the squares inside the brackets. Remember that f is your announced forecast, so it is known before the match. The variable we don't know before the match is r, which indicates its final outcome. So R is our random variable or vector here, and the expectation must be computed regarding its elements. Our question is now, what is the optimal forecast, say F star, that you should announce as your forecast in order to minimize the expected Breyer score we will get for it? We can see that the expected score is a quadratic function of f1, f2, and f3, so we should be able to find the point f star that minimizes the expectation of S by differentiating this function with respect to f1, f2, and f3 and setting these derivatives to 0 to find f1 star, f2 star, and f3 star. To be sure this is indeed a minimizing point, we'll have to check the second order conditions for a minimum, and we won't do that here, but believe me, they are satisfied. Let's just rewrite the expression for the expected score as a function of f1, f2, and f3 using the properties of expected values. Deriving this function with respect to f1, f3, and f2 and setting these derivatives to 0 when evaluated for f1 star, f2 star, and f3 star, we obtain. It's not hard to see that these three equations imply that f1 star is the expected value of R1, f2 star the expected value of R2, and f3 star the expected value of R3. Now, remember that R1, R2, and R3 are random variables that may assume only values 0 or 1, and therefore their expected values for I being 1, 2, or 3 are 1 times pi plus 0 times 1 minus pi, that is pi, where pi is your probability, the one you really believe in that result I will happen. And that's not necessarily equal to the number you announced as your forecast. In conclusion, we see that f1 star must be equal to p1, f2 star to p2, and f3 star to p3. Therefore, we showed that if you want to minimize the expected Breyer score you receive from a probabilistic forecast we'll publish about a football match, your best strategy is to announce as your forecast the probabilities of each outcome you really believe in. This result concerning the Breyer score may be generalized for random events that assume one out of a finite number of possible results, and for random variables that may assume one out of an infinite number of possible results. For this reason, the Breyer score is called a proper or fair score function. A forecaster that tries to operate the system, meaning publish a forecast different than his or her probabilities to fool the Breyer score, will end, on average, worse off. The Breyer score is not the only proper or fair score function. In fact, any affine or linear transformation of the Breyer score is also proper. Other scoring functions that are also proper are the linear logarithmic, and the spherical, among others. The expressions showed here for these scores consider random events that assume one and only one result out of n possible results. So, the next time you hear a probabilistic forecast, not a prediction, from an analyst or expert from some field, try to score it using a proper score function once the event reveals its final outcome, and compare this score with the score of other forecasts. This will give you a better picture than just say, this forecast was wrong. Another takeaway from all this is the following. A better way to judge analysts would be to check their past forecasts and respective scores they got from them, since this will give you a good perspective on how they performed on the long term when providing forecasts on the subject they supposedly master. However, virtually no analyst publishes all his or her past forecasts, especially if they were far from the observed result. Some of them highlight only the forecasts for which they almost hit the bullseye. But this is what we call a selection bias, a good topic for another video.